We're going to talk today about exponential functions. This chart gives the population of insects over a period of time. You'll notice that time here has a pattern to it of +1, +1, +1, but the population has a pattern of ×3, ×3, ×3. When you graph this, you'll notice that you have kind of a little shape like this. Okay, and this is unlike what we've done before. Okay, your x values are your independent variables, and that needs to have an arithmetic sequence with it. And your y values are your dependent variable, and that will have a geometric sequence with it. Okay, so a function rule that describes the pattern. Now this is the pattern that I just used. This is the y values of the pattern of the example I just gave you. So a rule that describes this is f of x is equal to your first term, which is 2, then what your common ratio is, which in this case was ×3, ×3, ×3, and then x, your variable, represents the number of times that happens. This is called an exponential function, and the reason because it's called exponential function is because the x is an exponent. Unlike quadratics where the x is squared, or linear where the x is just plain right in line with everything else, this is exponential. And how do we use these? All right, if it says the function f of x is equal to 500 times 1.035x models the amount of money in a certificate of deposit after x years, how much will there be there in 6 years? Okay, so I put a 6 here in place of the x and then tap it out on my calculator, and we find that there'll be $614.63 in there in 6 years. Okay, it's just that easy. Here's one that, and on that last one, you saw that the money was growing. We started with, oops, get rid of that. We started with $500, and we ended up with $614. So our money was definitely growing. Here it says that the population is 200,000, and it's changing like 0.98. So I'm multiplying it by 0.98 each year. And what will the population be in 7 years? So I multiply it by 0.98 one time, and that'll give me after 1 year, and then 2 years, etc. So we put a 7 up there and we do it, and it's down to 173,625. Okay, you'll notice on that one it went down. All right, it's got to be something to do with this right here. That one went down, this one went up, and we'll talk more about that when we talk about exponential growth and exponential decay. Okay, and again, in order for this to be exponential, you have an arithmetic sequence here, and you have a common ratio here. So they're multiplied. The basic format for this would be right here, okay, where A is going to be the value you start with, B is going to be your constant ratio, and X is the number of times that this occurs, okay? All right, so here's some examples. Let's take a look at these. I've given you ordered pair for each one, and then I've taken the ordered pair and put them into a chart. You'll notice with each one of these, the x values have an arithmetic sequence. +1, +1, +1, +1. So it's really all about the y's that determines if it is an exponential function or not. In this case, you had +64, +64, +64. That is an arithmetic sequence for the y's. That makes this one linear. So these points right here belong to a linear function, belong to a line. Here, again, this is the same. Here it went -1, +1, +3. Well, I definitely know it's not linear, but I might try it and say, okay, what's the difference between these two? +2. What's the difference between these two? +2. That is your second difference rule, which makes this quadratic. All right? So this one is quadratic. And then for the third one down here, we've got, again, +1, +1, and this one's times 0.5, times 0.5, times 0.5, or times 1/2, or divided by 2. All of those would give you a constant ratio. So this one is going to be exponential. All right? And you should be at the point that you should be able to tell the difference between those three. You can look at a graph. So if you were to graph this, you do just like you do any other graphing. Let's pick some x values and put them in here. You can do this on your calculator. Don't forget, when you put a -1 in here, that actually makes that 1/2, which is going to make this 1/4. Okay, put a 0 in there, and you'll see it starts out kind of slow, and then it gradually turns and gets higher. This is a curve. This is what exponential functions look like. They look like a curve, but there's several different curves that they can be. It can look like this, all right? Or I could take that and I could reflect that, and it would look like this, okay? That's two scenarios. Let's erase this, okay? It could look like this, okay, with the values going down, or it could look like this, okay? So there's actually 4 different ways that this could look. So let me kind of help you with those, all right? This kind of just gives you a summary of what's going on there. If the b value is greater than 1, okay, that means that whatever's happening is like getting larger. The values are getting larger, okay? If the a value is positive, it opens up, kind of like the a value with our parabolas. Our parabola opened up. If the a value is negative, then it's going to open down, okay? But the curve will look like this. One will just be going up, and the other one will be going down. All right, if your b value is between 0 and 1, so if your b value is a decimal or a fraction that falls between 0 and 1, then as you increase the x values, your y values are going down. Okay, this would be if the a value is greater than 0. Again, that'll open up like that. And if the a value is negative, then it'll flip down like that. Remember that negative is just like a reflection. Okay, and that's it.